Hi, everyone. Thank you all for joining the first episode of this new series we're calling For Dummies. In this series, we've started from a desire to understand the underlying science concepts from projects across the center for people who don't have a background in that particular field, so that we can go off and attend center seminars and talks and have a better idea at what all these talented people are actually doing, and also hopefully to inspire your own work. So the way that we are structuring these sessions is our presenter is going to give their talk, and if you have any questions, we would like you to write them in the Slido so that you can see the QR link on the slide, and also I've put it in the chat. And we're doing that just so that the questions can be anonymous and you can, feel comfortable writing whatever you want. Any questions, big or small, no matter how dumb you think they are. It's kind of the point of this whole series. And we will read out the questions at the end. And yeah, it's not going to be too long of a session. And yeah, I'll welcome Carl, our first ever presenter for this new series, who is going to talk to us about clouds and radiation.
Great.
Can I just quickly add one thing about the Slido?
Yeah.
Sorry, Carl.
Yeah.
But you can also vote on questions that you like, and we can read out those ones preferentially if they get upvoted. Cool. I just wanted to add that.
All right, great. Thanks, Greta. Yeah, so I'll be talking about clouds and radiation. I've another comment on the whole topic that I guess I've had to make a bit of some assumptions about the dummy level. And so a lot of this for some people might be very obvious and you might have learnt it in way back in old undergraduate days. Some of it might be something, as Emma was pointing out, that people just completely missed in all the education they've done up until now. And so I'm happy to sort of, if there are any very basic questions, things that I've missed, then very happy to discuss those. If anyone would like to have discuss some more detailed, complicated nuances of these topics as well, then you can also have a go at doing that. So yeah, hopefully this is the very least, it might spark some inspiration to some people and increase your understanding or appreciation for this area of science. And yeah, and that everybody finds it interesting. So well, there we go. Before I go any further, I just wanted to flag these three readings here as sort of options to read into these topics further if you feel like you want to, just increase your understanding further, or if you want to go after this and just double check some things. This textbook on the left is a great resource as well, obviously like a textbook resource to go over some of the detailed scientific information and understand some of the nuances of each of these topics. The IPCC assessment reports are a great source to sort of show how these areas are currently being researched and what the current state of knowledge and state of the climate is regarding these things. And then I also wanted to put this book here on the right, which I found very, very interesting and useful for understanding this. And it's kind of like halfway between a popular science book and a textbook. And so it explains a lot of these concepts in plain language, but also includes lots of relevant equations and figures as well to help you. Okay, so we'll start off with thinking about the radiation side of things, and in particular, Earth's basic radiation budget. And so you have radiation coming in from the sun, and this is in approximate equilibrium with the radiation going out. Obviously, climate change puts this out a little bit, but for our purpose, we just think about this budget being in balance. And the radiation going out from the Earth is determined by the Stefan-Boltzmann law, which I have here, where the temperature of the radiation emitted, the energy emitted, is proportional to the fourth power of any object with a temperature. So if we imagine the Earth starting off at 0 degrees, solar radiation coming in, the Earth or any other object heats up until it gets to a certain temperature where that outgoing radiation is equal to the energy of the incoming. the incoming radiation is intercepted by the Earth by like a flat disk. That's the 2D representation of how this radiation is actually absorbed. Obviously, the Earth itself is a 3D object, and so the relationship between a circle and a sphere, which is 1 to 4, then determines how that total radiation that is received at the top of the atmosphere from a nadir viewing point, which is this solar constant. Now that then is sort of spread over the whole globe. And so we get down from about 1,360 watts per square meter to, on average, 340 watts per square meter over the entire globe. There's one other important point to note is that not all this radiation is actually absorbed. About 30% of it is reflected. And so the amount of absorbed radiation from the sun on average over the whole globe is 240 watts per square meter. And this is sort of captured nicely by this figure here from the IPCC, which I'm sure is familiar to lots of people because it's used all over the place. And I find this figure very useful for just going over each individual component and using it to sort of check your understanding regarding what process is actually occurring at each point, how the numbers all add up together, and just as if there's anything that in here that you don't quite understand, or this is a great way to sort of try and put everything together. So from this Stefan-Boltzmann equation, we can go into a little bit more depth, think about how this equation is actually an integral of a more fundamental process represented by the Planck equation, which describes how an object at any temperature or at a given temperature emits radiation across different wavelengths. So what this is showing here that as an object increases in temperature, not only is the total amount of energy being emitted increasing, but the wavelengths that are being emitted are also going down to shorter wavelengths as well. So now if we think about this and we apply that to our energy budget perspective, we have radiation from the sun, which is coming in at one certain spectrum of wavelengths or distribution of wavelengths, and then radiation that is then emitted by the Earth at different wavelengths. And even though these are totally different wavelengths, they have very different properties, they are both in balance. And so then we think about what's actually going on in the atmosphere, and while we don't have smooth distributions, but these jagged bits, and also how the greenhouse effect works. Individual sort of molecules and species in the atmosphere absorb radiation of different wavelengths in different ways, sort of based on their molecular structure, which determines these vibrational modes. And so we can see these very polar molecules like H2O, water, and methane are very polar. They've got their charges distributed around, which means they're able to absorb radiation in many different vibrational modes at different wavelengths. And so they're very efficient greenhouse gases. So we can see in particular in this figure on the right, water vapor up the top here is absorbing quite a lot of solar and terrestrial radiation. So it's a very effective greenhouse gas. Where CO2, you can see it has less vibrational modes. It's a less effective greenhouse gas, although obviously more important for other reasons. And hopefully everybody can imagine or was able to attend the annual workshop last year and could see Christian and some of the other members doing the greenhouse dance. And if you ever see that or can bring that to mind, then you'll never forget how this effect works again. And so the important point here is just that we have different gases that absorb and emit radiation in discrete bands. The final part of the whole radiative story is scattering. And so that's where radiation, instead of being absorbed, it just scatters or reflects off something, whether it's a molecule or a solid object. So the scattering the type of scattering that occurs, or the scattering regime, how it's often described, is determined by the relative size of the object doing the scattering and the wavelength of the radiation that is being scattered. So if we look at these two wavelengths here of our solar and terrestrial radiation, and compare that to some different objects in the atmosphere, so air molecules and cloud droplets, can think about the different types of scattering going on. And so first, we imagine solar radiation interacting with air molecules. We're in this Rayleigh scattering regime, which sort of causes this blue light to be scattered and causes the sky to be blue. Think about the same solar radiation instead interacting with cloud droplets, we get geometric scattering, which is why clouds are so bright and why they reflect so much solar radiation. We can go through the same thing with terrestrial radiation. Doesn't really interact much with air molecules, and so there's not much scattering going on, as you can expect. And then finally, it undergoes this Mie scattering with cloud droplets. And so the important point here isn't to know exactly what's going on in each of these scattering regimes, but to just think about how the way that radiation and matter interacts depends heavily on both those absorption spectrums I was showing before and those vibrational frequencies, and also these different types of scattering. And so we'll relate that at the end to how different types of radiation interacts with different types of clouds and why we get these very different effects. Moving on to the cloud side of things, starting off with just some basics of water vapor and evaporation. So any surface of water will naturally undergo some level of vaporization based off just the proportional to the temperature. And then any vapor that's in the air will also naturally undergo some kind of condensation proportional to the mixing ratio or partial pressure, which is essentially the amount of water vapor in the air. If we introduce some kind of source of energy, we can increase the temperature or just increase the amount of vaporization going on, introduce more vapor into the air. As this air obviously ascends in the atmosphere, we have temperatures going down. As the temperature goes down, that rate of vaporization is going down to the point where we reach this equilibrium, the saturation vapor pressure. We get the formation of clouds, and that energy that we originally put in at the surface, which didn't change the temperature because we changed the phase. Now we're back to the same phase, which means to maintain the energy balance, we then release that energy up here, which is why it's referred to as latent heat. That the latent energy is released. Thinking about this in a very basic log P skew T kind of plot, which some people I'm sure are very familiar with, other people maybe get confused by all those different lines and arrows. Essentially, the important points are that at the surface here, we have an amount of water vapor and a given temperature. We can represent this by the dew point temperature and the actual temperature. As we go up, the dew point remains the same because we're not changing the amount of water vapor, but the temperature is going down until, again, as I was describing before, as the temperature is reducing, that amount of rate of vaporization goes down until we get past this equilibrium point, and then we get the condensation is exceeding vaporization, and we get cloud growth. And then again, that energy is being released, and so this then feeds more ascending and convection. We imagine now what's specifically going on when that vapor is condensing into liquid. I'm imagining two different scenarios. One where we just have individual molecules come together and form a droplet. We call this homogeneous nucleation. It's just water vapor molecules going to water vapor or water liquid drop. Whereas before, when we were talking about the saturation vapor pressure and the relative amounts of condensation and vaporization going on there, that was regarding a flat surface. Now we have this very tiny spherical droplet, which has much more of its surface area exposed to the air, which then means that we have much more vaporization going on from this surface because of the increased surface area exposed. And so even if we do get homogeneous nucleation happening in the atmosphere, this almost always just leads back to forming water vapor again because it can't grow fast enough to get past that small spherical point. And so the way that nearly all water droplets actually grow from vapor form is by first condensing onto something like an aerosol particle. See now, because this particle is much larger, The surface of this droplet is now much more like the flat surface that we were thinking about before where we define our saturation vapor pressure, which then means that the droplet is able to effectively grow without immediately having all that vaporization occurring. And then there are many, many, many other processes that go in between here and forming a sizable cloud and eventually forming raindrops. And then obviously have different types of rain and different types of clouds being formed by all these different processes. But this gives you an idea for the basics of how things get started. So now sort of using this knowledge, we can think about clouds having these three different properties: the amount of water per unit volume, amount of water through a whole column, and then the amount of water droplets per unit volume. And then these three properties all affect how this interacts with radiation. And the most common way that we describe this is through the optical thickness, which is essentially how much radiation is depleted as it travels through a cloud. So if you were to just shine a torch through a cloud, how much light from that torch would come out on the other side? Basic way of thinking about it. And so if we think about all the different ways these properties can affect the optical thickness, you just imagine a basic cloud here with a certain amount of water, a certain number of droplets. We increase the number of droplets, there's greater surface area of the water exposed that then scatters the radiation more, increases the albedo, and then increases the optical thickness. Another way we can increase the optical thickness, fairly obviously, I think, is just by increasing the liquid water path, having a thicker cloud. And so the important point here is that we have the same liquid water content, so the actual mass of water per unit volume in all these clouds is the same, but the way that it interacts with the radiation is very different. So now putting all these things together, we'll go through the different ways both the short-wave radiation from the sun and long-wave radiation from the Earth interacts with clouds of different type, and then how that actually affects the weather and the climate. So firstly, if we imagine a low cloud formed just by the basic boundary layer processes, these are low in the atmosphere, so they're fairly warm and also have a fairly high albedo because of all the water in them. And so because of that high albedo, they reflect lots of incoming shortwave radiation. Because they're low and warm, they also emit lots of shortwave radiation, which again, all comes back to that Stefan Boltzmann relationship, where because it's a warm cloud, it emits lots of radiation from it. If we think about a cumulonimbus cloud, this is very optically thick. It reflects lots of incoming radiation. Not much shortwave radiation is transmitted through it. And then because the top of the cloud is so high and so cold, it doesn't emit much long-wave radiation either. Finally, a high cirrus cloud, because these are so thin, they don't reflect much incoming shortwave radiation. And also because they're so cold, they don't emit much long-wave radiation. So if we sort of put all these components together, we can think about how this affects the atmosphere and ultimately the weather and the climate. So these low clouds, they have lots of outgoing shortwave radiation, lots of outgoing long-wave radiation. So essentially lots of outgoing energy from two different types of radiation ultimately causes cooling. With our tall cumulonimbus cloud, we have lots of outgoing shortwave radiation, which can cause cooling, but also not a lot of outgoing long-wave radiation. And so this typically causes warming. And so the effect that this can have can be mixed sort of depending on other specifics and where and when these are occurring. Finally, the cirrus cloud, which can be quite paradoxical because it doesn't reflect much shortwave radiation. So the outgoing shortwave is low, and also because it's not emitting much long-wave radiation, there's not much energy being emitted in general from these clouds. So actually this cloud's can have a warming effect. So I think this sort of summarizes a variety of key interactions between radiation and clouds. Obviously, there are many, many other types of clouds and other ways that we can think about how radiation interacts with these, but this is a great place to get started. So hopefully everybody's learned something from that. and we can have a discussion about any questions people might have.
Awesome. Yeah, thanks for that talk, Carl. I loved all the diagrams.
Great.
Um, let's start off with some questions in the Slido, while people still adding more. The first one we have here is what, so this is back to how molecules scatter radiation, but what are the molecules actually doing when they scatter radiation if they're not doing the greenhouse dance?
Yeah, so the greenhouse dance bit is um, so that's when you have this matchup between the wavelength and that sort of vibrational frequency, and so it's like almost like a harmonics kind of thing. The scattering, it's it's a lot harder to explain because it depends on the specific type of scattering that you're talking about. And so actually, I mean, the optical scattering is probably the easiest one to explain because I'm sure people have seen those diagrams where you have a droplet of water and you've got the light going in, it's being sort of scattered and then going out and producing things like rainbows. And so in that regard, it's the scattering is just produced by the sort of basic sort of reflecting and bouncing around that how we often think about light.
Mhm.
The Rayleigh scattering and the Mies scattering, I'm not actually sure if I know specifically what's actually going on there, except how to it's often the way that these are described is the amount of forwards and backscattering that they each produce. And so when this kind of scattering is occurring, where is the radiation going, which is important when you're doing like radiative transfer calculations, um, and also how much scattering is occurring at those different amounts. So like with in regards to like why the sky is blue, that's because Rayleigh scattering, which is the type of scattering that's going on with this type of radiation particle interaction, that is proportional, it's inversely proportional to the fourth power of the wavelength, I think, or might be slightly different to that. But essentially, that the scattering is much, much stronger at shorter wavelengths, like blue light compared to the longer wavelengths like red light, which is why we get more scattering in the blue wavelength, less in the red.
Mhm.
I think that's probably all I can say about those. I don't, regarding what is actually happening physically in regards to the process. Um, yeah, that's probably a question for a physicist.
So it's like depending on the what the molecule looks like and how far apart it is from like how yeah what the molecular structure is, it'll either absorb the radiation and like wiggle or it'll um like reflect it or scatter it somehow.
Yeah, and so you're gonna have to think about like a few different things at once, but and treat these separately. Yeah, and the way that you sort of put all these things together and calculate things like the radiative transfer is by sort of adding all these things up. And so like the amount of if you imagine like a path of radiation and how that's being depleted along a line, or well, even more than that, how that's just changing along a line. And so um, if you look up the important equation here is the Schwarzschild equation. That sort of describes how radiation is both sort of being absorbed, how it's being emitted, how it's being scattered, and then you sort of how that's happening all the way along a path. And you put all those things together, and that determines the total change in radiation along that path.
Okay, cool. And what was that called? Sorry, the
Um,
the you
that's
mentioned the
the
equation or
I'll get it up because
okay.
I need yeah. He did lots of different stuff, this guy, and lots of stuff on like general relativity. And so, yeah,
Right.
I get confused with the work you did there.
Oh, did you want to jump in, Bethany?
Yeah, if Carl doesn't mind, maybe I can try and talk to a little bit to scattering.
Yeah, please.
Cool. Okay. So I guess the fundamental difference is between the Rayleigh and the Mie scattering is that Rayleigh scattering um, is in is a relationship between the size of a particle and the things it can scatter, right? So in the case of the atmosphere, or in this kind of scattering, a small particle scatters wavelengths that are much larger than it. And it just so happens in our atmosphere, the size of the atoms and molecules in our atmosphere cause this scattering process that results in all the other wavelengths, be like the short wavelengths, being scattered and us having a blue sky. And the thing about it is it's this wavelength dependence. There's a for a given particle, that particle will scatter a particular wavelength. And so you can have a situation maybe in a different planetary atmosphere where that scattering, or like subatomic particle sizes, where that scattering happens for other wavelengths. But in our atmosphere, it's the interaction of our molecular gases and the resultant wavelengths that get scattered give us that blue sky. So the fundamental thing about it is that wavelength relationship. Mie scattering is happens when the scattering object is much, let me get this right around, is much larger than the wavelengths. So it's almost like you can kind of conceptually think about it as all different wavelengths in the atmosphere hit a really large object and they bounce off it because it's a bit like them banging into a wall. And there's no wavelength dependence in that. That's the key difference between the two. Because it happens with really large particles, there's no wavelength dependence in that Mie scattering. But Rayleigh scattering has that really strong wavelength dependence.
Wouldn't that be geometric scattering?
Yeah, pretty much. Yeah.
And then Mie scattering is the in-between one, where it's
and that's where you get that kind of when you think about it in having in clouds and why clouds look white to us underneath, it's because there's no wavelength dependence of that scattering, and so what you see is white. Right? If there was a wavelength dependence of the scattering, you would see one preferred wavelength, and for us, that would be a color or something else we could detect in the infrared. But the reason that we can tell just visually with our own eyes that scattering is independent of wavelength is the fact that the resultant color is white, which is a mixture of all wavelengths.
Yeah, that's a nice way of describing it.
Very cool. We have a couple more questions in the Slido, so I might read another one. And the scattering one was my question, so hope I didn't take too much time. How does ice versus water clouds fit into the picture of cloud radiation interactions? Right, so I guess if the
I
cloud is
didn't
icy or
go
watery.
into ice much because just to keep it a bit simpler. And probably the first point to make is that often ice is associated with very different types of clouds, and so thinking about the all these different types that we have at the end here, and so cirrus clouds, not only are they made out of ice, but also they're so thin that that's actually the more important point, the fact that they're so thin and is more important than whether it's water or ice.
And sorry, the cirrus clouds are the really high ones?
Yeah, so they're the ones on the right here that are really high. But yeah, I think also, I'm actually not certain about this. I just realized it's probably just an assumption that I make because it's associated with cirrus clouds. But I think ice is also just less reflective than water, the same, keeping everything else the same.
So that would change the optical depth of the cloud?
Yeah.
There's a bit of a geometry component to it as well.
Sorry?
So I think there's a bit of a geometry component to it as well because liquid droplets are spherical. And so they have this nice symmetric property that depending on they'll have the same interaction with instant radiation, irrespective of what angle it comes in on them. But ice crystals are linear, and so the interaction of radiation with an ice crystal is dependent on what we call the incident angle of the radiation. So what angle the radiation is coming in. So I think that's also why you get a bit more variability in those interactions. And it's also why you get cool optical phenomena like sun halos as well.
Yeah, and there are loads and loads of these that I can never remember exactly what the radiation ice interactions are and why sometimes you get obviously you get rainbows and double rainbows and halos and I can't remember the name of all the others. And I can never remember specifically what types of scattering and reflectance is going on at each individual time. Yeah. Maybe another important point to make as well is the fact that even though often we talk about like reflectance and albedo, what's actually going on in the clouds is multiple scattering. And so the particle comes into a cloud and it sort of scatters around in lots of directions. And then because of that, we get lots of that radiation being scattered back out to space. It's not just as simple as a cloud acting like a mirror and it just comes in and then bounces off.
And there's also, like, if you have a cloud that's icy and watery, then I think I didn't quite understand the bit about latent heat, but I imagine if you have an icy and watery cloud, the latent heat does slightly different things, right? If you have like melting and freezing.
Yeah, well, I mean, going from liquid to ice or water or vapor to ice is another phase transition. And so in that case, so it's easier to think about it in terms of just going from water to vapor back to water, because the energy that's going in at the surface then has to be the same amount of energy that's then being released at the top. And so you can do your basic energy balance there. And then the other thing the other important point is that with ice, you can get liquid drops freezing in a few different ways. They can freeze homogeneously, or they can freeze onto ice droplets, or they can freeze onto an ice nucleating particle. And so you get a liquid to ice phase transition. Or you can have water vapor depositing directly to an ice particle, and then that's a different phase transition as well. So, yeah, so in all of these phase transitions, there's energy. There's always some kind of energy being released and absorbed. It's when thinking about the latent heat, and this is what's going on most of the time. When we think about the important convection that happens in the atmosphere, it's because of this liquid to water to liquid again. Go ahead, Bethan.
Yeah, I was just going to add to that as well. The latent heat of the water vapor to liquid and reverse phase, the value of that is a magnitude stronger than the freezing and melting phase. So what's going on in the lower troposphere when you start to form clouds and actually go through your condensation process, that's far more important energetically to the troposphere and to the further development of that cloud than it is when you get higher up and you start to go through freezing processes.
Right.
Yeah, thanks for confirming that. I think that's my suspicion, but I wasn't actually sure what the precise value was for that latent heat. Yeah, which is why obviously when we talk about convection and latent heat release, we're always thinking about the water, and when we talk about the ice phase, it's more that's quite important for the formation of raindrops. And actually, I think there's an interesting fact to learn and take away from today, actually, that something like 80% of rain that falls on the earth starts out as ice, just melts before it reaches the surface. And so ice is very, very important for the growth of raindrops. Like I was suggesting before, that there's many, many processes going on between water vapor and then growing to an actual drop that falls on the ground. But yeah, regarding the convection that goes on in the atmosphere. It's that water phase that's the important bit.
Mhm. And just to check, in this diagram, the latent heat, that's the heat released because as the water evaporates. Is that right? Or the heat absorbed?
As it condenses, yeah. So you just think about things from an energy balance perspective. Well, I always like to imagine things as like the pot of water on the stove, because it's very easy to think that you've got energy going in at the bottom, and then at some point, um, everything has to reach an equilibrium. And so as you're putting energy into the water and and the temperature's going up, it's going up because there's an imbalance in the energy budget. So there's energy going into the water. Then when it reaches boiling, temperature won't change anymore, because instead all of the energy that's going into there is being used to, well, the energy is being used to convert it from water to liquid water to water vapor. But then you've still got the stove on. You've got all this energy going from the stoves. Then you have to think, where is all that? I'm burning all this gas. Where is that energy going? And where that energy comes from is then once that water vapor, if we then condense that back into a liquid, that energy that would have otherwise been used to convert something to heat is then, that's why we call it latent heat. That latent energy is then released, and so then it does become heat.
Okay. Okay.
Or the way that I like to think about it as well, if you want to imagine what the particles are actually doing, it's a little bit like when um, if you imagine like throwing a ball at like a trampoline compared to like a piece of Play-Doh or something. If you have a molecule of water that is so if it's going from vapor form to liquid form, it's in this high energy state. And then when as it then condenses back to water, it's then going into this low energy state. And so then that energy is being transferred.
Okay, so
Yeah, so at all stages along, you have to think about where the energy is going and how it's being conserved.
Yeah. Okay.
Cool.
Um,
We might have time for one more quick question, I think. One more science question, and then we also have a fun question. But this one's about aerosols. Do you know what the most common aerosols are for cloud nucleation? And are these affected significantly by human activity?
I'll start with the last one because it's a simple answer. Yes, it's that very heavily affected by human activity. Probably the most interesting feature of that is ship tracks, where we see ships going across the ocean and the emissions they release. They contain lots of aerosols, and so they produce quite a lot of clouds. And one you can imagine is like around like factories, they produce a lot of aerosols, a lot of clouds coming from that. So yeah, there's like lots of different ways that human activities produce aerosols and therefore influence clouds. The main types of aerosols, so it depends very heavily on where you are. I don't know exactly what their relative concentrations are, but sea salt from like sea spray is a big one, especially over oceans. Depending on the region, again, over oceans, different biogenic aerosols are very important. And so if you've ever watched one of Alana's presentations, she goes into detail a lot about the different types of biogenic aerosols produced over the Southern Ocean. There's also a great paper, like a summary paper that Mark Mallet wrote, sort of going over all the current state of understanding about aerosols in the Southern Ocean, and that's got this great diagram. It's got lots of description about how all these aerosols are produced. Over the land, it's more things like dust and pollen that are the key aerosols. Trying to think of other ones that I'm missing. Sulfur dioxide is an important anthropogenic one, so that's kind of what you get from like the ship emissions and from factories and things. Like black carbon from like burning fossil fuels. I think the way that atmospheric scientists often think about these is just as like aerosols as being a homogeneous group of particles, and that's all there is. But when you look at the work that people like Robin Schofield or Rob Ryan do as atmospheric chemists, um, then there's this huge array of different types of aerosols, and that some of them are just like single particles, other of them are more chemically active, and so they undergo they're important for chemical processes in the atmosphere too. And there's this huge school of study that's quite interesting and very, very significant to the atmosphere because of the effect that it has in our clouds and therefore the weather and climate, sort of regarding the specific aerosols. And so I definitely recommend reading more into that and if you're sort of interested in that topic. But I think that a lot of atmospheric scientists are a bit lazy and just think about aerosols as a homogeneous group.
Interesting. Yeah. Okay. Well, our final question. Do you have a favorite type of cloud?
Do I have a favorite? Yeah, well, we Melbourne Uni did a what do they call it? An away day at the end of last year. It was just like it went to this like centre nearby and did some activities and some like a short writing workshop and a short group activity. And as part of that, we had to like do a survey on various weather and other just related topics. And one of the questions was, what is your favorite cloud? And I said the cumulus congestus cloud because I always think they look interesting. Probably isn't the most interesting cloud, I don't know, maybe from a physics perspective, because there's all these really, well, probably the most common one that people say when you ask them this question is lenticular clouds, because they, hopefully a lot of people know what I'm talking about, but they have this incredible feature where they are actually um, produced in a stable atmosphere. So they are not buoyant. They don't want to lift up. They're only being lifted up because they're going over something like a mountain. And so if you have like a mountain here, you have the cloud being forced to form at the top. You can see there's someone putting something in the chat. Hopefully it's a picture of a lenticular cloud, maybe. Um, and so you get this sort of UFO cloud that's hanging stationary in the air. So those are quite cool. I like the cumulus congestus because they're just like extra fluffy and very well defined, and they always like make the nice photos.
Mhm.
But actually, I actually not the best at identifying all those like hundreds of different cloud types. I read that book recently on how to spot the different types of clouds. And it's got a fun from an amateur's perspective, but from a scientific perspective, often we just think about clouds in terms of how much ice is in them, how much water is in them, how high are they, how thick are they? And so I think as scientists, we're often a little bit boring, and it's the amateurs that have that more romantic relationship with clouds, where there are all these different types and these very, very rare ones, which have these very interesting kind of looks.
Well, yeah. I just looked them up. They look really pretty. Also kind of look fake.
I think Bethan's put a link to one as well. Thanks for that, Bethan.
Yeah.
Do you have to be a bit careful now when you look for lenticular clouds because there's a lot of actual fake images. The ones that are like stacked 20 pancakes deep.
Okay. Got to find them in real life then. Yeah,
Yeah.
okay. That's kind of all we have time for. Thank you, Carl, for your presentation. And thanks everyone for sticking around and asking questions. Yeah, we're hoping to do this as a regular series, and the next one should be in a few weeks. And we're going to be learning about Rossby waves from Kyle at ANU. So look forward to that. And I'm also going to encourage anyone who's keen to put their hand in and try presenting one of these to, yeah, be brave and have a go. It's a good experience and, yeah, hopefully a lot of fun. Yeah, okay.
Great. Thanks so much.
Thanks,
Great.
Carl.
Thanks a lot for
Thanks everyone
coming.
for coming.